Hello everyone. We have talked about dot product, which try to measure how two vectors align to each other. In this video, we will try to do something kind of opposite, and instead for measure how two vectors align to each other, we will try to measure try to generate an oriented surface, or a small oriented surface patch from two vector. So let's think about we have two vector like here. For example, here is A, and here is the vector B. We would like to try to generate a small surface patch from A to B, like so. You can think about a vector A slowly going to B, or in the opposite way, a B slowly the vector B is slowly trying to align with A. And in this mental picture, you can think about two vector pointing into two directions. If they slowly turn into another, slowly trying to align with another vector, it kind of generate a surface patch that is a plane. So we can think about we will use the wedge product to define such operation. We denote the wedge product as this symbol. So we can write vector A wedge, and now we will looking to some property we want this wedge product have. For example, we can think about let me see properties. So we can think about A wedge and B should equal to minus B wedge A, because we would like this wedge product have some sort of orientation. And in this case, in the wedge product is always has two choices. The orientation only can be opposite each other. A better word to call it, instead of orientation, handness is a better way to call it, but most people don't use it, so we will just still use orientation. And from this property, from this property, we can easily see that if a wedge product itself, C wedge Z, for example, doesn't matter where vector C pointing, but if a wedge itself is equal to 0, because it have to equal to Z wedge minus Z wedge Z, and this equation can be only satisfied when C wedge Z is equal to 0. In addition, we will also like to have a distributive property of this wedge product. So we can have A plus B wedge C plus D are equal to A wedge C plus A wedge D plus B wedge C plus B wedge D. And the last property, we will not use it, but we just introduce it just for completeness, is that when A wedge B, we first do the A wedge B, then wedge C, vector C, is equal to A wedge that we first wedge B, wedge C. Yeah. And sorry, and this and this will represent oriented volume in 3D, but we will not introduce it we will not use this relation in our courses, but just nice to mention it. Now let us look at the wedge product in 2D case. As usual, we use orthogonal bases, so E1, E2. Then we express any vector into E1, E2. So we can think about E1 is pointing on this direction, and E2 is pointing on this direction, and they are 90 degrees to each other. So the dot product between them is 0, and they all have length 1. Now let us say that we have two vectors, vector A and vector B, and they have A1, A2, A1, E1 plus A2, E2, and we have B1, E1 plus B2, E2, and we wedge them, and we can express A into their into our basis. Then let us see what is the wedge product become. So A1, which A1 is equal to 0, but I'm still going to write it out such that we can cancel them later. And now we have A1, E1, wedge, E1, wedge E2. Then we have A2, E2, wedge B1, E1, A2, E2, wedge. I usually write them in here, and E2, wedge E1. And then we can have, and then what we left is A2, E2, wedge B2, E2, A2, E2, wedge. Wedge. 2 into. So we said the same wedge, the same vector wedge itself is always equal to 0 because it does not generate any surface. So these two guys go to 0. Then we left with this is B2. Then we left with A1 B2 equal to E1 wedge E2 plus A2 B1 equal to E2 wedge E1. And we know that E1 wedge E2 is just equal to minus E2 wedge E1. So we would like to express them into this form. Just E1 E2 minus A2 B1. We choose to use E1 wedge E2. For people familiar with the cross product, you can see for people familiar with cross product, you can see that this A1 B2 minus A2 B1 corresponding a parallelogram. So if A is pointing to this direction and B is pointing to this direction, this is A, Okay, let it be longer. Yeah, B. Then this number here is corresponding to the area of this parallelogram. As you can see, if you're familiar with cross product, since we have in 3 dimension, here you usually correspond an arrow pointing up, pointing in the third axis, which we don't have in 2D. But this time in geometric algebra, this one is not a vector. It's something we call a bivector. Instead for have like cross product in 3D have a vector the perpendicular like E1, E2. We don't have a vector perpendicular with E1, E2. We have bivector instead. So you can think about, in this case, is E1 and E2, and this corresponding the little surface patch, the oriented in the counterclockwise manner. So let me try bigger. E1, E2. So it's oriented in this way. Last video, we talk about that the number we get, for example, a wedge B is equal to A1 B2 minus A2 B1 E1 wedge E2. We said that the number here is representing the area of this parallelogram. This is correct, but our question is that with the same bivector, does it represent a unique parallelogram? The answer is a spoiler answer is the answer is no. But let us look into it. Let's say we have we have 4 different vector. We will study the case A wedge B, and here was a C wedge D, and we all see that they are pointing into a different direction. And in our case, we first focus on the case here. Let us calculate the bivector. And we have A wedge B. We have A wedge B. Then we we can see it from here, since A wedge A is only E1 and B has E1 and E2, then this case is quite obvious. The answer is square root 2 divided by 2 E1 wedge E2. That's the answer. And here the case is now C wedge D, and C is only E2, and we have D equal to the minus square root over 2 divided by 2, square root of 2 divided by 2 E1 plus square root 2 divided by 2 and E2. And since E2 wedge E2 is over 0, then we get what we get is that C1 wedge C wedge D is equal to minus square root of 2 divided by 2 and E2 wedge E1. And since we would like to express it into the same bivector basis, so we will use it E1 wedge E2 instead. Then we have to cancel the minus sign, so we will go to E1 wedge E2. So the thing we got, so the answer we have is that A wedge B is equal to C wedge A and C wedge D. So this actually means that the bivector, the wedge product come out from the bivector, does not represent the shape. Does not represent the shape of the area. So we can think, of course, if we draw it into a parallelogram, the number here is the area of the parallelogram, but the bivector doesn't fix the shape. So more correct way to think about this bivector is a wedge. Let's say a wedge B, and A is like this, and B is like this, and what a wedge B represent is like a surface patch that oriented in this direction. So they oriented in this direction, and the shape is deformable. So we can change the shape, since here the parallelogram is different parallelogram, and yet we have the same bivector. The bivector itself actually representing the shape. No, sorry. The bivector represented the surface patch and the orientation, but doesn't represent the shape. Now we talk about wedge product in 3D. As before, we use orthogonal basis. We use E1, E2, E3, and you can think about E1 point to that direction, E2 point to this direction, and E3 pointing up to the direction. And remember, this is a 3D. They are all orthogonal to each other. We choose them such that they are orthogonal to each other. And this representing a 3D arrow, which we call it vector. And because they are orthogonal to each other, so anyone that dot product with another product that is not itself is equal to 0. If a dot product is with itself is equal to 1, we choose the length to be 1. So we start with two vectors like A and B, express them into this this equation, express into a orthogonal basis like A1 E1 plus A2 E2 plus A3 E3. So let's see what does it become when we what we will become when we wedge A and B, vector A and vector B. So we expand into our orthogonal basis. Then we get we just wedge them term by term. Then we get A1 B1 wedge E1 wedge E1, and A1 B2 E1 wedge E2, and A1 B3 E1 wedge E3, and you get the same idea. But since we know that in wedge product, any vector wedge itself is equal to 0, so this is 0, this is 0, and that is 0. So what is left is that A1 B2. So what is left is that the wedge, the vector wedge another vector that is not the same vector, and we left with basically 3 different kind of bivector. So we have E1 E1 wedge E2, we have E1 wedge E3, we have also E2 wedge E3. So let us first focus on E1 wedge E2 or E2 wedge E1. So it's basically these two. We focus on these two first. So we can write up E1 B2 minus A2, no, sorry, A1 B2 minus A2 B1. We use E1 Wedge E2. We need to remember why we can write it like this is because E1, let's say I E which is equal to minus E J which E I. So remember this rule. Do you remember this rule that in the beginning of this video? So that's the reason we can do that. And the same story carry on. We focus on E2 wedge E3. It's A2 B3 E2 wedge E3 E3. Oh, sorry, no, it's minus. Now it's this one. This one is the A3 B2. A3 B2. We write it into E2 wedge E3. So we have calculated this and this. What we left is calculate this and this, because they are both sharing the same bivector but the direction is opposite. So we will flip the E1 E3 to E1 wedge E3 into a E3 wedge E1. So it will become plus, I'm afraid I don't have enough space, but hopefully it will not happen. So A3 B1 minus A1 B3. So we have E3 wedge E1. For people who are familiar with cross product, you may realize that you get basically the same formula with A cross B, vector A cross A vector B. You will get almost exactly the same formula, except this one will become vector 3, and this one will become vector 1, and this one will become vector 2. But such that these are representing a normal vector, or a normal vector that perpendicular with A and B. But we are not doing here because the normal vector is only defined on 3D. And in higher dimension is difficult to see. I will not say only defined in 3D, but in higher dimension, it's difficult to see to interpret the normal vector. So instead for normal vector, we don't think about normal vector. So, oh, sorry, maybe do it like this. We don't think about normal vector. We think about the orient surface patch. The orient surface patch that generated by E1, E2, the orient surface patch generated by E2, E3, and the orient surface patch generated by E2, by E3, E1. But as I said, as I may have maybe mentioned in the very first video, if you don't know about the cross product, it's fine. You don't need here. Yeah, you don't need this knowledge here. We haven't talked about what does it physically mean to adding two bivector with different bases. Two bivector together. First bivector is E1 wedge E2, and second bivector is E2 wedge E3. What does it mean to adding them together? As we have mentioned before, the bivector itself does not represent a particular shape, but representing orient the surface patch. But the shape of the surface patch is not fixed, but the area is fixed. So here I use I imagine that the A1, the A, E1 wedge E2 is like this, and I represented a surface patch, and the normal vector is pointing to the E3, E3, like a normal vector. But the normal vector here is really for the visualization purposes. Yeah, because I'm still drawing everything on 2D, even though we are talking about something in 3D. And it's the same with the second one here. The second vector is a B, E2 wedge E3. Then we have, I imagine that these orient surfaces rotating from E to 3 based on this orthogonal basis vector. And then I also use normal vector to visualize, to give you a better visualization. And this is a 90 degree to this surface, to this oriented surface patch. So the question is, what does it mean when we plus them together? Then do you remember we can deform the bivector if we like? So we can, in this surface, we can draw it in this way. The area is still A and it's oriented here, right? And this, we can draw it in this way. Maybe here is better. No, here. Yeah. And it's rotating like this. The normal vector still pointing out in more E3 into into E3, and this surface, surface, the normal vector is pointing right. This is E1. Since we can deform them, and now one important is that we change that such the way the length of this length and this length are the same and point to the same direction and share on the same direction, but in the opposite direction, but in the same. I don't want to say axis because we are not using coordinate, but in the same direction but opposite. Yeah, so it's not in the opposite direction. Yeah. So when if this length and this length are the same, I know we are always choose them to be the same because we can always, for this area to be A, it depends on this length and also this length, right? So we can always change them. We can always change this length such that this length and this length will be the same. Same with this length, we can change them. Since we can deform the bivector area. We cannot deform. The area is fixed, but the orient, the surface patch, the shape of the orient surface patch, we can free to deform them. So when we add them, what we mean is here, such the area still is A. I think I would drop the A. You get the idea. N plus this. So I just attach this attach this common direction. So it's here, 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 here. And very important that these two directions cancel each other and they have the same length. So what you end up with is you can imagine a surface, a surface like a plane crossing these two edges and have an oriented in this manner, going down and pointing the normal vector is pointing in this direction, and then 90 degree, the normal vector is 90 degree to this surface. Yeah, it's a bit difficult to draw. Yeah, but I think you get the idea. So one trick to add them together is that you're trying to make them share on the same direction and using in the same direction, but in the opposite way. And then you use this common direction to, so it's this one, this common direction, and then with this direction and this direction is a common, just opposite to each other. Then you merge them together. Then you follow the shape, and you ignore you ignore this axis and this axis. Ignore the E1 and E3, then try to line up with them, because you're not ignoring, but if your vector go here to here, is corresponding a vector go here, right? From the vector go to this direction and vector plus go to this direction is corresponding a vector go to that direction. Then you just draw a new vector, and then you connect with the vector that you cannot cancel, and you create a new surface patch. So to the end, you are creating a new surface patch, like this one. Now we talk about wedge product in n dimension. We're still using a vector with two different vectors to generate orient the surface patch with a wedge product. So we have orthogonal basis from E to E1 to En, and they are orthogonal to each other, and they are also normal with itself, which means has length 1. And we can express any vector into these bases in n dimension, and let's say A is the sum of the AI, EI, and B is also the sum of the BI, EI. We are not going to write up the expression for A wedge B, since they have an n much dimension. But this time we are interested on what's the different combination, a total number of different combination can happen when given dimension n. So think about when you have so when think about when A wedge B, right? You can have you just write the C when E1 wedge E2 and plus D like E1 wedge. Okay, let's say C1 and C2 and wedge E1 3 and plus dot 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 dot, dot plus E1 wedge and something here and something here, okay, let's say Cn and E1 wedge En, right? And then you will plus D1, you will press a D1, let's say D1, just a scalar, and E2 wedge E3 and plus dot 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 plus to the D and D minus 1 here, let's say, yeah, D minus 1 and E2 wedge En. So we are interested in how many such bases will to the end will exist. So since now we have n different choices, and we take 2 from these choices, and we're not putting that, and permutation does not count, so we are looking for the combination of 2 in n different choices. So this gives us the equation called the NCR. In our case, we have R always equal to 2 because it's a bivector. We're interested in the combination of a combination of the wedge product between two vectors. And the NCR have formula. The NCR have formula like this: n factorial divided by r factorial and n minus r factorial. So in 2 dimension, in 2 dimension, this means that n is equal to 2 and r is equal to 2. Then we have n, we have 2 factorial with 2 factorial and 0 factorial. 0 factorial is 1, and so here is equal to 1. It makes sense because in 2 dimensions we can only have E1, which E2. There's no another choices. Case n is equal to 2 in this case. Okay, if we have n equal to 3, then we have 3 factorial equal to 2 factorial and 1 factorial because n because 3 minus 2 is equal to 1, then equal to this is equal to 1 multiply 2 multiply 3. This is 1 multiply 2, and that is just 1, so we get 3. It makes sense because we have one. We can only have 3 choices: E1 wedge E2 and E2 wedge E3, or E3 wedge E1. So yeah, you get the idea. Then you can just R is always equal to 2, but if you're working on R is always equal to 2, doesn't matter dimension. Now you can work out how many bivector bases you can have. You can use actually how many bivector bases you can use in any n dimension. But one thing we can, I think I just erase here. One thing is quite important to mention is that in 4 dimension you can have wedge like a E1 wedge E2 in like the case n equal to 4 in 4 dimension plus b E3 wedge E4. Such combination of a bivector, you will never. Such combination, you will never find any. Okay, I'm not using A and B, and let's say using C and D. You will never find any 4-dimension vector A and 4-dimension vector B. It's not possible because you can try to work out the algebra. Such expression is never possible. You will never get this E1 wedge E2 plus something the area of the orient the surface patch in E3 E4. The reason, for the geometrical reason, we are not going down into the algebraic reason, which you can, but here the geometrical reason is that, remember, we adding 2 bivector together, right? And then we kind of generate another. Since this goes this and this goes this, so we kind of generate a new surface patch that are 90 degrees to this new first surface patch. This can never happen. In this case, E1 wedge E2 plus E3 wedge E4, it can never happen because they don't share the same axis. And no matter how you flip them, we can always flip by changing the side, right? But no matter how you flip them, you can never find any single one sharing the same. Not I try to avoid the word axis, but I just use it again. Yeah, I use you will not find any basis vector here to pointing into the same direction, yeah, or opposite of that direction, because E1, E2, E3, E4 are pointing into different direction, and this should argue that why you can never get you can never get this kind of expression by wedging a four-dimensional vector A with a four-dimensional wedge B, because this does not represent orient surface patch. But this happened in 3D and also this happened in 4D and higher dimension. You don't have to worry about in 2D and 3D. You don't have to worry about this case happen, because in 2D you have only one bivector. So this is no problem at all. Because in 2D you can only have one oriented surface patch. Yeah. But in 3D you can only have three, but no matter how you do that, you always find that at least you always find that they overlap, because you no matter what's the combination, you always find them overlap. Because if you here, then if the E2 overlap with the E2, if you have a E3 that overlap with E3, then no matter which one you pick and which another one you pick, you always find that one of the axis, no, one of the not axis, one of the direction, it will overlap. Now we talk about wedge product is not invertible. This means that if we have three different vector, let's say that A wedge B, vector A wedge with the vector B equal to vector A wedge vector C. And we know, given that they are equal to each other, doesn't mean, I mean, put a question mark, doesn't mean vector B is equal to vector C. The short answer, the spoiler answer is not. But let's see why. We consider the case in 2D. Just consider the case in 2D. Let's say A is equal to A1, E1. We pick our basics vector such that parallel with the vector A. This means it will be 0 for the vector E2. And then we will have vector B equal to B1, since you already decided the basics vector to that the E1 align with align with A vector A. Then this has to be B1 and B1 E1 plus B2 E2. And if we do the wedge product, A vector A wedge vector B, then you will have E1 B2 A1 wedge sorry, A1 B2 E1 wedge E2. And you can see that B1 does not matter. So doesn't matter b1, you can always end up this equation, this bivector. And the reason is that, let's say we have here, this one is A, and let's say this is B. And if we have a parallel line, that the line is parallel with vector A, or different vector, like, okay, this is B, this is also can be, this also can be, every single of them will give you the same wedge product, every single different B. Because over this line, since we know this direction is E1, right? And this direction is E2, right? And this direction is E2. So the if B changing, the vector B is changing over on this line, the only thing is changing is B1, not B2. And since if you look at this equation, look at this expression, B1 is not involved. So so B1 can be anything to give you the same bivector. This conclude that B, the vector B, not necessarily can, but not necessarily equal to C. Yeah. So generally, this is not true. This is not true. So vector B equal to vector C. No, this is not. And of course, we have only proved the case in 2D, but it will be the same if we have n dimension. So we can choose our basics vector, A1, E1, but B will be the sum of BI, EI, I equal to 1, sum to n dimension, and you do this, is equal to you will always find a list of bivector, but you will always find that B1 is not involved in the expression. Which is basically the same interpretation that B1 can changing over the parallel line with respect to A and still give you the same wedge product.